Hi, everyone. My name is Petar Veličković, and I'm a research scientist at DeepMind. And I will be giving you an introductory presentation and Colab exercise to the vibrant and exciting field of graph neural networks. As we go along, I will also be telling you a lot about fantastic graph neural networks and where you might be able to find some of them in the real world. So in this talk, we will be going through neural networks that operate over graph structured data, which are commonly denoted as graph neural networks, or GNNs for short. I will start by giving you a bit of a motivation for why you might want to work with data that lives on a graph, and also overview some of the standard techniques that have actually already made us go a really long way. So the motivation for why you might want to study graphs is that graphs are actually everywhere around us. You can see them in lots of data that just comes around naturally. All chemicals can be represented as molecular graphs. Transportation networks can naturally lend themselves to a graph representation. Social networks, such as this Facebook friendship graph, can be represented as a graph structured. And even places such as brain connectomes, where you might not immediately expect a graph to appear, can be meaningfully represented as a graph structure in one way or another. In a way, you could say that, especially because graphs naturally generalize objects such as grids or sequences, where machine learning has already made very significant strides, you can say that the data that comes from nature is really nicely captured using a graph. Therefore, if we want to advance scientific discovery using neural networks, it makes sense to study data that lives on a graph. And to kick off this discussion, I would like to just dive into the molecular example. And as mentioned, molecules are very naturally represented as graphs. You can divide them into atoms that are connected by bonds, and those easily correspond to nodes and edges in a graph. You can attach features to every node, such as atom type, charge, or bond type to edges, and so on. Once you have a molecule represented in this form, you can ask yourself some interesting questions about the molecule. And something that might be very interesting is whether this molecule represents a potent drug. So one thing you can do is, once you have your molecule, you can train a graph neural network to predict a binary task. Will this drug inhibit a certain bacterium, such as Escherichia coli, for example? You can train this on a curated data set where you have a bunch of molecular compounds, and you know how strong this bacterium will respond to the presence of the drug. But once you've trained this graph neural network to give you an answer, you could, in principle, apply this model to any molecule, not just the ones that you've curated in your data set. So if I have a large data set of known candidate molecules that are known to exhibit some drug-like properties, you can feed them through your model and look at the predictions, like how likely it is to inhibit the bacterium. And you can take the top 100 candidates from the model and send them to chemists for more thorough investigation, maybe with some additional filtering. And what you might end up realizing is that the chemists have discovered here a previously overlooked compound, halicin, that ended up behaving like a highly potent antibiotic. So this sounds like a very interesting discovery. So you end up getting it published in a journal like Cell. But then, because you've used this fairly straightforward machine learning pipeline to come up with completely new therapeutics, these kinds of discoveries quickly get picked up by outlets such as Nature, and then outlets such as the Financial Times, BBC, and so on and so forth. In a way, this is one of the most popular successful applications of graph neural networks to date. If you've read any articles about scientists discovering powerful antibiotics using AI, you can know that there is a graph neural network hidden in there that operated over the molecule. Similarly, you can look at transportation maps, such as the ones you might find within Google Maps, and those can also be naturally modeled as graphs. For example, you could put nodes in the intersections of the traffic network and put edges as the roads connecting them. And you can put some node features in there, such as the length of the roads, the current speeds that vehicles are having, or maybe some historical speeds that they had at this point in time. One other way in which you can do this is partition the route into these super segments, which model a part of the road. And this now gives you a natural graph structure that you can operate over. So if I then run a graph neural network over this super segment graph, I can predict interesting things about the travel route. And one very interesting thing you can predict there is the estimated time of arrival. So in a way, it corresponds to graph regression. Given the graph structure that corresponds to the road, I want to predict what's the expected travel time over this particular path. And we ended up developing the system at DeepMind, and along with our partners at Google Maps, have successfully scaled it up to a model that is now actively deployed within Google Maps. And in several major cities, it's drastically reduced the proportion of negative user outcomes when querying for what's the expected travel time. In some cities, such as Sydney or Taichung, the improvement is over 40%. And therefore, it's another very impactful application of graph neural networks that's already impacting many users worldwide. Another aspect that you might want to focus on are social networks and recommendation systems more specifically. So the basic task of recommendation is based on preferences that a particular user might have, reliably recommend new content for the user to explore. You can use existing links, like what are the things that some users find interesting, how do different concepts relate to each other, as some adjacency input to a graph neural network that can then predict new links. One issue is that most of the standard methods, at least up to a given point, have assumed that you process and feed the graph in all at once. And there's been quite some research on how you might be able to run these graph neural networks on very large graphs. And one of the first approaches, GraphSage, showed that you can basically subsample some neighbors and subsample some neighbors' neighbors, and only run your graph neural network over this reduced graph of subsampled neighbors. And if you let this model train for long enough, you will end up with performance that is quite competitive to having the whole graph in there in the first place. And when this gets scaled up to the billion node level, this has been applied in the PinSage model, which directly tries to model the Pinterest graph and predict new ways in which visual concepts that the users have found interesting can map to new things that we might want to recommend to them. And this graph has 3 billion nodes and 18 billion edges, and therefore corresponds to the first web scale popularized application of graph neural networks, which is currently deployed actively within Pinterest. So hopefully these techniques motivate you to explore graph representation learning and graph neural networks as a great approach for dealing with the kinds of data that nature usually throws at you. Assuming we have that motivation, let's think about how we might go on and develop our own graph neural network model. So what we actually want is something that sort of generalizes a convolutional layer, because we can think about graphs as a strict generalization of images. If you have any image data set, you can treat the image as a grid graph where every node corresponds to a pixel and its 4 or 8 immediate neighbors specify the adjacency matrix. Convolutional neural networks leverage the convolution operator to exploit this strong spatial regularity in images, and it would be highly appropriate if we could somehow generalize this to operate over arbitrary graphs. So just as a quick reminder, how convolutions work on images is we're able to exploit this spatial regularity to define a comparably very small matrix of parameters k, which is then slid across the different positions in the image. And at each step, we just take local pairwise position product sums, which allows us to specify an output image that detects patterns in the original image. And because this is just one operator that's applied everywhere in the same way, it's going to capture very important invariances such as translation invariance. So an object of interest is interesting no matter where it appears in the image. And also it exploits locality. So a pixel is far more likely to be related to the pixels right near it rather than pixels in opposite corners. So what we really want when we try to define a graph convolution is something that's quite similar, something that considers the immediate local neighborhood of a particular node and uses that information to further update the node's features. So if I have features in a central vertex B in this case, and I have features of its immediate neighbors, my graph convolution layer needs to predict the next step features of this node, HB prime, which is some function of the entire set of neighbors of node B. So we basically need an operator that looks at over sets of neighbors to derive next step features. And there's quite some challenges with deploying a graph convolution in this way because there's a lot of desirable properties that a convolution layer needs to satisfy. It should ideally require no more computation and storage complexity than it takes to store the graph itself, which is number of nodes plus number of edges. It should have a fixed number of parameters regardless of input size. So if I give you a graph that is twice as big, or equivalently in convolution neural network land, if I give you an image that's twice as big, you should ideally not have to increase parameter count. So I can apply the same graph convolutional layer on graphs of arbitrary sizes. It's very nice to have the localization property, so to be able to act on a local neighborhood of a node only. And it's nice to be able to specify different importances to different neighbors simply because they might not all be equally relevant. And ideally, we might want the layer to be applicable to inductive problems. So if I apply my trained graph convolution layer to a graph it has never seen during training, a completely new structure, it should still nicely generalize to that structure, assuming they both came from a similar distribution. And fortunately for images, this highly rigid and regular connectivity structure of each pixel connected to its 4 or 8 neighbors makes such an operator very easy to devise as this small matrix that you slide across the image. Arbitrary graphs pose a much harder challenge. And one thing that is also quite important to keep in mind before we dive into how you might design layers like this is once I have a layer like this, what can I do with it? So imagine that you have an input graph with features xi in each of the nodes and some adjacency information, usually specified as an adjacency matrix A. Once you apply your graph neural network layer, it will exploit these local interactions to update the features of each node to this latent space H. So each node will have features hi representing the latent features of that node that are somehow mindful to that node's direct neighborhood in the graph. And once you have these vectors, you can do lots of interesting tasks on a graph. You can do node classification, so classify each node independently by just applying a shared layer F to each one of these H vectors to get predictions in each of the nodes. You can do whole graph classification if you aggregate all of the H vectors for all the nodes using some permutation invariant function, such as summing. So you can take a sum of all of your H's and then apply some module to predict an answer on the whole graph level. And finally, you can do predictions over edges, or in some cases, even prediction over whether links exist or not, by taking the features of the two vertices that you want to investigate the edge over. You might also have some edge features attached to it, which is this Eij vector. And once again, you can learn a shared function that applied to every edge or potential edge in your graph performs the required prediction. So there's a wide variety of standard tasks that you can specify on a graph, and it's important to keep those in mind when applying graph neural networks. We will primarily focus on node classification, but it's useful to note that these are also a potential choice to investigate. With that being said, let's dive straight into ways in which we can define these different graph convolutional layers. We will work our way slowly towards a very simple way in which we can update node features to be mindful of the entire graph. We will assume for simplicity for now that we have an unweighted and undirected graph. And this means that our adjacency matrix will be binary and symmetric. So you either have a 0 or 1, depending on whether there exists an edge with a particular pair of elements. And if I is connected to j, j must be connected to I as well. Once we have a matrix like this, you can look at the effects of multiplying your node feature matrix H by the adjacency matrix. This effectively recombines the information in the neighborhood into just one vector, through the virtue of this matrix multiplication operator. And usually it's useful to also leverage the power of deep learning, so actually giving some layered processing of the features. So besides multiplying by the adjacency matrix, we will also multiply by some learnable linear transformation W, which corresponds to just a linear layer in a deep learning framework. And we might want to apply some nonlinear functions such as ReLU to further make our feature representation more complex as we go along in stacking these layers. Before we can call this a complete graph convolutional layer, we need to fix a few issues. First of all, if it's not explicitly enforced, this update rule may discard the central node, and therefore your predictions for a particular vertex would drop the context about that vertex itself. So you can make a very simple correction here by adding the identity matrix to your adjacency matrix, and this enforces that node I is always connected to itself. And this allows you to rewrite this rule as basically sum pooling. So you get the next step features of node I as first taking the sum over all the neighbors of the features of that neighbor multiplied by the linear transformation W. And finally, you can apply a nonlinearity such as ReLU on the result. This is called sum pooling because you're pooling all of your neighbors with the summation aggregation function. This might come with a few problems because multiplying by the adjacency matrix may increase the scale of the output features. Basically, if you sum 6 different things that have roughly the same distribution as you do, the features in the next layer are going to potentially be very scaled up. So as a result, it's often useful to normalize the adjacency matrix and force the features not to explode. And one very common way to do this is to also multiply by the inverse of the degree matrix, where the degree matrix tells you the overall degree of each vertex along the main diagonal, and it's 0 otherwise. So multiplying by the inverse degree basically amounts to taking our original sum pooling rule and further dividing by the degree of the receiver node. So we have this division by the neighborhood size of I plugged into the formula. And this is now called mean pooling because we're effectively taking the average of all of our neighbor features. This is quite simple, but quite versatile and usually a very strong choice for inductive problems. Instead, we can try to normalize the adjacency matrix in more interesting ways, and one very popular approach performs this idea of symmetric normalization, where instead you multiply by the inverse square root of the degree matrix from both sides. And as a result, what you're actually doing is you're dividing by the square root of the product of neighborhood sizes of I and J. This update rule is often called by just graph convolutional network, or GCN, popularized by Thomas Kipp and Max Swelling at ICLR 2017, and it's currently the most popular graph convolutional layer. It's quite simple to implement, quite scalable and powerful, and as a result, most commonly cited paper in the literature. But there are still some limitations of this model that might be interesting to address moving forward, especially as the graphs get a little bit more complex. So first of all, we assumed this adjacency matrix that's binary, symmetric. We had no way of easily attaching complex features to the edges, which, for example, for computational chemistry might be problematic as edges can have multiple bond types. And one way in which we can correct this issue is by instead focusing on edge-wise mechanisms. And in the most generic form, what this means is that we can compute messages, that is arbitrary vectors, that get sent across edges of the graph. And you can condition these messages by any edge features that you might have. And then we can think of the aggregation function as just aggregating all the messages sent to it, as mentioned, using something that is permutation invariant. So this is embodied in the message passing neural network model from Justin Gilmer and others, where you compute a message function from node I to node J, which takes into account the features of the sender vertex I, the features of the receiver vertex J, and any edge features you might have along that path, and computing basically a vector of message that's being sent along this link. Now, a vertex, what it has to do is it needs to collect all the messages sent to it and aggregate them using some permutation variant function, which can, for example, be summing, as we discussed before. And then that is recombined with the information already present in that vertex. So that's why there's the hi vector in there. And that goes through some readout function to get the next step features for that particular node. Altogether, this gives the message passing neural network framework, which is a very powerful and generic framework for dealing with graph structured data. And the message function and the readout function, these FV and FV elements, are usually themselves smallish multi-layer perceptrons. So they're fairly simple computational modules. In order to visualize what message passing neural networks are doing, let's consider this example of a graph with 6 nodes, where on each node you have attached a certain feature vector. And let's say I want to send a message from 3 to 4. I will take the features of 3 and I will take the features of 4. I've deliberately omitted the edge features here to make the illustration more simple. And I will compute the message from 3 to 4 as a result of applying the message function FE on these two. In a simple and similar way, I can also compute messages from all other nodes that get sent to 4, and I aggregate them together, for example, by summing them up, as is displayed here. And then combined with the inner features that were previously in node 4, I can take the summed message, pass it through the readout function FV, and this gives me the features for that node in the next step of processing, which I feed back into the node for the next step. And this process is carried out in parallel over all the vertices. Here we visualized it just for node 4. So the message passing network that I just presented is the most potent graph neural network layer, at least in terms of layers that look at only first order neighbors. However, it requires us to store and manipulate these edge messages, which can get costly both from a memory and representation point of view. Like it could overfit if the data is sparse, and it could end up using a lot of memory if the graphs are big. So in practice, these MPNN models are often only applied to small graphs or graph datasets where it is assumed that there's some pretty complex manipulation going on over the edges. You can think of them almost as MLPs of the graph domain. As some intermediate approach, let's go back to what we did in graph convolutional networks, where we aggregated just the sender node's features, hj, potentially after being transformed by some weight vector. And then there was this coefficient, alpha ij, which said how much are node j's features important for node I. What the GCN did when they defined the 1 over square root of neighborhood I, neighborhood j, was they defined this coefficient explicitly. So they explicitly said, based on the graph structure, this is exactly how much node j is important to node I. But there are many possible factors other than graph structure that influence the importance of a neighbor to another vertex. So it might be quite useful if we can compute this coefficient in a slightly different way. And in the graph attention network model, which I have proposed with a few others at iClear 2018, we instead compute this coefficient alpha ij implicitly. So for a particular edge, we take the features of the sender, the receiver, any edge features, and we pipe them through this attention function A, which gives us coefficients along pairs of nodes ij, which we can then normalize using a softmax function across the neighborhood. And this A can be any learnable shared neural network, which is often called a self-attention mechanism. So for example, transformers fit within this paradigm. And as a result, we arrive at this graph attention network update rule, which using some tricks such as multi-head attention, we can usually significantly stabilize in practice. They're probably not as general as MPNNs. The theory is still under development, but they can be more trivially scaled up compared to MPNNs because this attention function only computes one scalar, the influence of node I to node j. And in contrast, the message function had to compute a vector message along each edge, which drastically increased the potential memory requirements of the model. So here's a way to visualize what's going on in a graph attention network. On the left-hand side, you have the attention mechanism, which looks at features of a node I and its neighbor j, and some attention function, which then computes the coefficient alpha ij, which signifies the influence of node I to node j. And then on the right-hand side, you can see the multi-head attention mechanism, where each colored line indicates a different way in which a node 1 in this case, receives information from its immediate neighbors. And then that information is directly aggregated and across different heads, either concatenated or averaged to produce an updated representation. One more note I would like to make on transformers, which are a very popular model for dealing with sequential data, is that very often there is a bit of a debate as to whether transformers should be used instead or together with graph neural networks. Depending on the perspective you're looking at the problem, you can actually make the claim that transformers are graph neural networks. If you imagine them as operating over a fully connected graph of all pairs of input tokens, your message function being just the sender node features and the aggregation function being attention, you can express transformers as a special case of message passing neural networks. And because they operate over a fully connected graph, they actually don't exploit any structural information in the model itself. You have to externally inject it into the model, and this is what transformers do through the use of positional embeddings. If you were to drop the positional embeddings, you would end up with something that's basically equivalent to a fully connected graph attention network model. And you can think of the attention coefficients as sort of inferring a soft adjacency matrix for some graph that nicely describes how your data is operated. If you want to see more detailed exposition of how this is derived, I would invite you to take a look at Chaitanya Joshi's publication in The Gradient. So now I would like to walk you through a Colab exercise where we are going to go through the elements of implementing some standard graph neural networks over one of the most standard benchmark data sets in a way that anyone can easily work through using just a simple Colab and not even requiring any special GPU resources. What we will do is perform node classification on the standard Cora benchmark. Cora is a citation network that classifies nodes, which are papers, into different topics. There's 7 different topics, and there's 2,708 of different papers connected by about 5,500 edges. Features corresponds to bags of words that represent the paper, and we're given only 140 training papers and access to 500 validation papers, which then will make us have to generalize to about 1,000 test nodes in the graph. And what we'll do in the Colab exercise is implement the sum pooling, average pooling, and the graph convolutional network update rule. And if you're interested in improving further, you can try to explore any of the other ideas that we have covered in this presentation. So I'm going to now bring up my Colab screen, where we're going to build several standard graph neural network layers on top of the Cora citation network dataset. Cora is a standard benchmark for graph representation learning, and due to its very small scale, it's easy to quickly train on it even when you only have a CPU at your disposal. This is what made it propel many of the early papers on graph representation learning. While today it is known to be oversaturated, so if you actually want to perform academic research in graph representation learning, some other data sets like the Open Graph benchmark would be recommended. This is still an excellent playground for coming to grips with some of the standard techniques in the area. So what we're going to do is we're going to start off by loading all of the necessary packages. I'm just going to pip install them just in case they aren't available. So we're going to need NumPy, we're going to need TensorFlow, and we're going to be using the spectral library for graph representation learning that we will only use for loading and pre-processing the data set in a nice form. So there's nothing spectral specific that we will be covering in this particular tutorial. So we're going to import NumPy, import TensorFlow, and import Spectral to begin with. And we will just wait a little bit for all of these to get set up. I'll make a new code cell as we're going along. Perfect. Spectral has these convenience functions that will allow us to quickly load and pre-process many standard graph representation learning data sets, such as Quora. And they come with these useful loader functions that will allow us direct access to items such as the adjacency matrix of the graph, the feature matrix, which gives us the feature in each of the nodes, and also the labels that tells us the topic of each paper. And then we also have access to these useful mask arrays, which tell us which nodes belong to the training set, which nodes belong to the validation set, and which nodes belong to the test set. And the particular function that we will call here is spectral.datasets.citation. And finally, we call load data with the dataset name set to Quora. So this will load the Quora dataset, pre-process it in a nice way, and give us access to all of these pieces of information in what is basically a one-liner. We will get these features and adjacency information in a sparse format in order to be able to deal with potentially large graphs. But for our purposes, we won't need the sparse representation. So we're going to immediately just convert both the features and the adjacency matrix to a dense representation. And also the adjacency matrix doesn't come with self edges. So as mentioned before, that's a common thing that we need to do at the very beginning. We add the identity matrix to the adjacency matrix just to make sure that this is okay. And in order to make sure that everything plays nicely with TensorFlow, we will convert the type of both the features and adjacency matrix to 32-bit floating point numbers, which are the standard representation in use for deep learning pipelines. Just to verify the size of the Quora graph, we will print out the shape of the features, and we will also print out the shape of the adjacency matrix and also the shape of the labels. So this will give us interesting information about the sizes of different concepts in our graph. And we might also be interested in how many training nodes we have, how many validation nodes we have. So because these masks are just given as a 0-1 array telling you whether or not each node belongs in the training set, in the validation set, or the test set, I can just print the sum of all of those masks, and that will tell me how many nodes I have in each three of these data sets. So if I were to execute the cell, it downloads the Quora dataset, pre-processes it, and now we have the Quora dataset fully loaded, and we can see that the Quora dataset has 2,708 nodes, 1,433 features in every node, and 7 labels, 7 possible paper topics. We have only 140 training nodes, which is a very low data training problem, 500 validation nodes, and 1,000 test nodes. So now that we have the dataset loaded in, we can keep going, and we will need to define 2 special functions that will allow us to do some of the standard deep learning loss and evaluation metrics, just in a way that is masked across this mask information. So cross entropy loss is a standard loss that you might apply when dealing with classification problems from some predicted logits from your network against some ground truth labels. But in this case, we also have a mask that we must apply. So what we will do is we will first compute the loss in every node, applying the usual cross entropy with logits function, and calling the appropriate inputs. Now we need to use the mask to only use the parts of this loss function for the nodes that belong in that particular set. So we first cast the mask into a float 32 type, and we additionally divide the mask by its average value, which will allow us basically to take a product of this mask with the loss and then take the mean of this product as the overall loss. And this now returns to us the cross-entropy loss over the nodes of the graph, but only taking nodes that are masked by the mask array. And in a similar vein, we might be interested in computing some accuracy metric. And once again, we don't want the accuracy over all the nodes in the graph. We only want the accuracy over, say, the test nodes or the validation nodes. So we need to mask appropriately. We first compute the correct prediction, which compares the argmax of the logits with the argmax of the labels across the feature axis. So this will tell us for each node whether or not it is correctly predicted by our model. And we can compute the full accuracy as just tf.cast of this correct prediction as a float 32, just to convert it back from a Boolean format into a floating point format. And once again, we need to cast the mask appropriately. And divide it by the mean. And now this allows me to take the individual accuracy elements and only multiply them by the positions that I care about. And now I can return the average across all positions to give me the accuracy only over the nodes that I care about. So there won't be any output for this particular cell, but it is important to specify it because we will need to compute losses and accuracies only over the nodes in a particular set, for example, the training set. Once we have this, it's time to define a very simple graph neural network layer. So a graph neural network layer looks at a node feature matrix, an adjacency matrix, some transformation that we wish to apply to every nodes, and an activation function. So what we do first is we transform each of our nodes using this pointwise transformation. This is the equivalent of the matrix W in the slides that I presented previously. And once we have these features that we want to aggregate, we will just perform a matrix multiplication with the adjacency matrix and these features. So keep in mind that this is going to be powerful enough to implement frameworks such as the graph convolution network, the sum pooling, the mean pooling, and the graph attention network, where you can basically express the graph layer as just neighborhood-based recombinations of node features. If you need to compute more complex edge functions, like in the case of message passing neural networks, this framework will not quite be expressive enough and some minor modifications will be necessary. But for now, we will be using this particular GNN framework because it is already going to encompass a lot of the interesting models that we care about. And it's very simple to write. As you can see, it's only 3 lines of code. So we transform each of the nodes individually. We matrix multiply with some appropriate adjacency matrix to recombine it across neighborhoods. And finally, we apply an activation function. So this is a general recipe for a large class of graph neural network models. Now using this, we can define a simple 2-layer GNN to classify the Quora dataset. So we have some features, adjacency matrix, some GNN model function. We can specify how many units do we want our neural network to compute in each node. So how many dimensions in our latent features, for how many epochs we want to train, and maybe the learning rate that we want to use. So we will define 2 graph neural network layers, and each one will have its own transform, for which we will use like the weight matrix W, which in TensorFlow terms is just a dense layer. The first one computes the hidden layer, which has a certain number of units, and the second one computes the classification of each node, so we need 7 outputs for 7 classes. Now we can define the GNN that's used to solve this problem on a particular set of features and adjacencies that first computes the hidden features in every node. So it applies our GNN function to the features, to the adjacency, using the transform that we first defined. And the activation function, we can use any nonlinearity, for example, ReLU. Then we can go on and define our logits by applying the second graph neural network layer, which starts from the hidden features and then the adjacency matrix, now applying the second transformation, which projects each node to only 7 outputs. And we treat these as logits, so there's no need to further transform them. We will use the identity function to just not transform anything. And the logits is what we return as our neural network's predictions. We are going to use a standard optimization pipeline using the Atom optimizer. So here we can load up some standard Atom optimizer, which has a learning rate equal to the learning rate we provided. And now we're going to do just a standard training pipeline with early stopping. So we're going to keep track of the best accuracy we've had on the validation data so far. And we're going to iterate over the graph data set for the specified number of epochs. We'll use a TensorFlow gradient tape to record all of the gradients as we go along. So we apply our Cora GNN on the features and adjacency to compute the predictions at this step. And we can compute the loss using the masked softmax cross entropy on the predicted logits and the ground truth labels. And in particular, we want to compute the loss on the training set, so we pass on the training mask. Once we compute the loss, we can specify gradients to update the variables based on this loss. So we first look at the variables that the gradient tape is watching. We define the gradients just by invoking the t.gradient function on this loss function using these variables. And finally, we can apply the optimizer to apply these gradients. So we call the apply gradients function on the zipped combination of gradients and variables. Finally, once we have updated parameters, it's useful to track validation and test accuracy. So we can take the logits as a product of our GNN using the features and adjacency after the gradients have been updated. And we can compute the validation accuracy as the masked accuracy on the logits against the labels, but using the validation set mask. And we can compute the test accuracy as well as the masked accuracy of the logits against the labels on the test set. Now, we should not be looking at the test set until we've firmly committed ourselves to the weights. So for now, we can only use the validation accuracy and compare it against the best validation accuracy we have received, which will update the best accuracy if we've exceeded it. And this should, in principle, save the current model so that it can be evaluated on the test set later. But to kind of skip the model saving stage in this Colab, I will just print out the statistics on this particular go. I'll just copy that line over here. So this will print the epoch, the training loss, the validation accuracy, and I'll just report the test accuracy here so that the last test accuracy that gets printed is the one that we're going for. So executing this entire cell specifies all the routines that we need to train on the Cora dataset. And now finally, we can just call one line of code to try to train on the Cora dataset for some particular given adjacency matrix. And we will compute 32 features over 200 epochs and use a learning rate of 0.01, which are some of the standard parameters you can use. Initially, I will pass the raw adjacency matrix to this function, which means I'm going to be multiplying my features with just the 0,1 matrix. Therefore, we're implementing sum pooling, and we're expecting this to have some problems with the scale of the features. And as a result, it might not give us the best result possible. Let's see what happens when we run it. So our model improves a little bit over the first 11 epochs, reaching an accuracy that is about 77.6%. And very quickly it converges to a good set of weights, so all the subsequent epochs don't update the validation accuracy. We're left with this 77.5% performing model. One thing that is very useful to verify here is that it's useful to use the graph at all. So what I'm going to do is test this by replacing the adjacency matrix with just the identity matrix. What this will do is it will basically render the operation of multiplying with the adjacency matrix as not really changing anything. So we just have basically a pointwise classifier in each of our nodes. So a standard MLP model that's shared across the vertices. And let's see if changing our adjacency matrix to this will affect the results in any way. So now you can see the progress is generally far more steady, but it doesn't actually end up surpassing around 50% or so. We will just let it finish to the end. But here you can see that if you're not effectively exploiting the graph structure, you're going to end up not completely capturing the interesting structure in your data, and this pointwise MLP will be unable to go beyond 50% testing accuracy or so. Now, once we've shown that the graph is actually useful by comparing these two kinds of models, we can try to explore more interesting kinds of graph convolutional layers. The first one we can explore is mean pooling. So we can first compute the degree matrix as the degree of each node, and then spread across the diagonal. And we can now rerun our train Cora setup using the features, but now we will divide the adjacency matrix by the degree matrix, which is equivalent to multiplying it with the inverse of the degree matrix. And this will now give us a normalized propagation rule, which should hopefully deal with any exploding signal that we might have. And this should hopefully be more stable than the update we had before. And as you can see, already after 30 epochs or so, it is behaving better than the sum pooling model. In fact, it has even exceeded 80 percentage points of accuracy on one of those runs. But the overall performance, which is around 78.7, is a more stable and strong improvement over the sum pooling model, which indicates that it is a good idea to normalize our adjacency matrix in this way. And finally, we will going to try out the specific version of the normalization that Thomas Kipf has proposed in the graph convolution network model. If you remember, this requires us to compute 1 over the square root of the degree and then multiply that on both sides with the adjacency matrix. So we can get the normalized adjacency matrix by first having this half normalized degree matrix and then multiplying that with the product of the adjacency and the normalized degree matrix. So this is the equivalent of taking d to the minus a half and then multiplying it with the adjacency matrix on both sides. Once we have this normalized adjacency, we can once again try to train on the Cora dataset using the features, using this normalized adjacency, and then same hyperparameters as before. Let's see how stable that is. So, in absence of the sum pooling aggregation, this model actually ends up usefully training for far longer. And it reaches, say, 50 epochs, and there's still some improvements. And you can see while on average you should not expect to see a very significant difference between this one and the division by degree, at least not on this data set. On this particular run, the test accuracy has exceeded 81%, which shows, at least empirically, this single run improvement on the degree normalized version, but both of them in principle improve on the sum pooling and are expected to perform roughly comparably in this particular setting. So this wraps up the Colab exercise that I wanted to guide you through. And we're going to quickly go back in the presentation to conclude this session. Thank you for following through with this Colab exercise. And in case you found any of the above interesting, I would like to point you to some potentially useful resources if you'd like to study these concepts further. All of these resources, which are in my opinion quite useful, I have recently summarized in a thread on Twitter, which you can directly find linked in the video description below. So I invite you to check that out if you're interested in more resources for learning about the area of graph representation learning. On that note, I would like to thank you for following my presentation and Colab exercise. I hope you have got some inspiration to tackle this exciting and rapidly emerging field of graph representation learning. And if you have any questions, please feel free to reach out to me either via email or via one of my other accounts online. Thank you so much.